Okay, let's carry on. So this is where I've got to before and I couldn't move the slide on. Everything's working now. So basically, by sizing the widths of the transistors according to the stack depths, we are restoring everything as it should be. So we can match the threshold for the unit inverter, we can match the drive strength, we can get the timing back to be what we want. So if you look at a NAND and a NOR and consider them, for the NAND gate, the P stack depth is 1, the N stack depth is 2. It's vice versa for the NOR gate. Now, we know the PMOS transistors are wider anyway. So the implication of that is that NAND gates are more compact than NOR gates. So the ratio in width is something like 73%. So it's about 3/4 of the size of the NOR gate. And that's because, of course, with the NOR gate, you start off with big PMOS transistors, then you double their size, which makes them even bigger. Whereas with the NAND gate, you're doubling the size of the NMOS transistors, and since they're the smaller ones, it has less impact on the area it takes up. So basically, NAND gates come out to be cheaper than NOR gates. So we've been considering T-sizing to match the drive strength. The other thing you have to think about is the gate as a load. So if the gate's a load, then if you T-size it, you're going to increase its input capacitance. So the stack depth of the NFETs is 2 for an AND gate. So WN is made twice that of the unit inverter. Then if you look at one of the inputs, so you look at the input A or if you look at the input B, but the inputs have a greater capacitance, as you can see from this equation here. Instead of being in the unit inverter, let me sort it here with a pointer. So yeah, in the unit inverter, the capacitance was essentially had a 1 + R as the factor, whereas now with the NAND gate, it's got 2 + R as the factor. All the other terms are the same. And so that means you've got a greater capacitance as a load. So if you connect a unit inverter to a unit inverter, the relative fan out was K out to be 1. But if you connect the unit inverter to the input of a NAND gate, what happens? Well, you've got the relative fan out for the NAND gate is this ratio FL NAND over unit inverter. We've just seen that that is essentially the ratio between 2 + R to 1 + R. So, of course, it depends what value you use for your ratio R. But if R is 2.7, then the relative fan out will become 1.3. Okay, so it's not a huge increase, but it's an increase. Of course, if your ratio R is smaller, 1.5, for instance, would be a bigger change. But you're talking about a change of the order of 1.5 in the relative fan out. And it depends on the stack depth. So of course, that was for stack depth of 2. If you've got a more complicated gate, you can end up with much bigger fan outs. Okay, so let's look at another example. So this one is a bit more complicated. It's not hugely complicated, but it's a little bit more complicated. So we've got 3 in parallel and 1 in series. We've seen this gate before. So this is 3 ORed together, and then ANDed with this, and then inverted, essentially. So when we look at that, so we look at what's going on in terms of the input relative fan out. What's going to happen to A and B? Well, if we do this transistor sizing, these ones have a size of 3 times the width of the unit inverter, WP. And these ones has a single times that, and these ones are all got a stack depth of 2. So remember that from before. So the width are 2 times W and 9. So once you've put in the T sizing, and you know what the widths are, you can then start working the relative fan outs. And so for inputs A and B, you get, well, you've got 3 here. So it's 3 Ri plus 2, because you've got 2 from down here. So this is for the NAND divided by the unit inverter, basically. So it depends what Ri is, of course. When you look at D, it's going to be slightly better because this is a smaller transistor. So it's 2 plus 1 times Ri. So what you can see that not all the inputs to our gate give us the same input load. So the relative fan outs differ depending on the path you take. So if we scale the outputs to the unit inverter, we change the inputs considerably. So if Ri was 1, which is a bit low, then ABC have relative fan outs of 5/2, 2.5. It's gone up quite a lot. And note again that the inputs are not all equal, so they can change. Let's look at another gate, okay? Because that was relatively simple. Let's look at something where something else would go on. And so we've got a Boolean expression. So we're taking A and B, we're ORing it with C. We're going to AND the output of that with D and invert the whole lot. Okay, so it's not a terribly complicated expression, but there it is. So how do we go about drawing this? Well, first of all, let's start off in the middle. So start off with the AB. So that's going to give us 2 series in the N tree and 2 parallel in the P tree. Then we've got the C input. That's going to be in parallel on the N side, so it's in parallel with these 2 transistors treated as a unit. Then again in series with AB treated as a unit on the P side. So that's the P side and the N side. We put in the C. Now we need to consider D. What happens there? Well, D is going to be, because it's AND we need to put it in series on the n side with the whole block that was there before, and in parallel on the p side with the whole block that was there before. So you can see how you build it up step by step. And then, of course, the output is always going to be inverted using this technique. Okay, now we want to t-size this. And we need to decide where we start. Okay. So one way of doing it is we can look at the deepest stack and do that first. So where do we find the deepest stack? Well, for instance, if we went from DAB, that's clearly the deepest on this side. We've got 3 transistors in a row, so we size them all to 3 WNI. So we've got these 3 sized at 3 times WNI. Then we've got 2 in a row on the other side. Now, how do we do that? We've got 3 as the width here. So what does that tell us about the width of C? Now, essentially, it works in a similar way to adding resistances in parallel. And you can see that because they're series resistors, but their resistance, their impedance, goes as 1 over the width. So if you're adding it, you're adding 1 over. So essentially what you're saying is 1 over the width of C plus 1 over the width of D is going to be 1. And if you do that, you work out that C comes to 1.5. Does that make sense? It's like adding in parallel. You're looking a bit puzzled. You've got 3. And the idea, what do you have to add to 3 to make it 1? And what I'm saying is that, let's go back, that essentially you're adding 1 over widths. So if you look down the left-hand side, you've got 1 over 3 plus 1 over 3 plus 1 over 3 gives you 1. And what you want on this side is 1 over 3 plus 1 over some unknown gives you 1. Okay, it's as I say, it's the same basic equation as adding resistors in parallel. So 1 over 3 plus 1 over x equals 1. So x is going to be 2/3. You then need to invert it and get 1.5 for our width. Okay, so that gives you this. Now you need to do the p side. That's relatively straightforward. You've got 2 in a row here, so they're width 2. That's also 2 in a row, so its width is 2. And that's a single, so it's WPI. Okay, so that looks relatively straightforward. And we can draw a little table, and we can design it with the WPs and WNs for A, B, C, and D, and get the different widths. But we could also have done it the other way around. So what happens if you start from the shallowest stack and do that first? So instead of starting DAB, we're going to start DC. But actually, I'm going to start even earlier than that because I'm going to start really shallow here. So that becomes 1, it's easy. Those are all 2s, same as before, no problem. But that's a 2 as well. So that gives you 2 WNI for both D and C. And then we need to work out A and B. And again, remember we're adding inverses. So basically the equation down here is D is a half. So half plus something plus the same thing gives you half. So half plus quarter gives you 1. So we end up with 4. So that's a different set of widths what we had before. And we can put the widths all together and see that you can t-size it in 2 different ways. So there isn't a single unique solution. And basically, it all comes down to whether you define D relative to AB on the n side, or whether you define D relative to C on the n side. But either way, you can get some very big gates. Okay, so we're ending up with the t-sizing for A and B being 4 Ni. And you could, of course, end up with quite big P transistors too, just as easily. So some libraries, and we'll look at libraries later, but essentially a foundry, which is a huge factory which produces silicon chips, will have its own library of all these different NMOS gates. And they use sublinear methods to keep this device size down. So what they say is widths of 4 or bigger just become unmanageable. And so one solution, typical thing to do, is just to square root it. And you can square root, of course, either one solution or the other solution. When you square root things, the differences between them aren't actually that big. 1.7 to 1.4s. Yeah, there are differences. What you can see is that your t-sizing is no longer a unique solution. You have to bring other considerations into what you choose. And what you find if you square root it, you still get a reasonable match to the threshold. It's not perfect, but of course you weren't going to get perfect anyway, because it depended on which way you looked at it, and that depends on which gates were high and low at the same time. If you reduce by, so say, square rooting it, one of the implications is the drive strength is lower. Of course, if your drive strength is lower, so also is the capacitance of the loads, because the loads will also be reduced. So to some extent, that isn't such a big problem. But you're always going to have this trade-off between speed and cost. And very often it's a matter of judgment as to whether your circuit or that particular gate, whether what you really need for that is speed, or whether actually you can sacrifice a bit of speed for cheapness to fit more of them in. And the answer you get will change depending on circumstances. There are other complications here as well. So at the moment, we've just considered the capacitance of the gates, of the gate electrode. Now, there are going to be other capacitances around. So for instance, the source and drain contacts have some capacitance, metallizations have some capacitance to ground. Everything is linked to everything. So think about the NOR gate. So nice simple gate you can see here. We know that Z and X will have parasitic capacitances. Okay, so this point here will have some metallization. It is a source or a drain, depending whether you look at A or B. will have some stray capacitance. Question is, how is that going to affect the timing of switching events? And we're not going to do a detailed calculation because it gets too complicated, but what we'll do is we'll look at some general principles. So what we want to do is consider the situation where B is low and A switches high to low. So if B is low, that means transistor B is conducting. Okay, so it's a PFET. You take the gate low, it'll conduct, and A is going to switch from high to low. So what happens then? Well, of course, the transistor A will turn on, and both CX and CZ, these two stray capacitances, will charge up from the power line up here. If you'd had the other way around, whereas to begin with A was low and B went from high to low, so it's just the other way around. So you're now saying that A is going to be fixed first, and then B is going to change second. Well, because A is conducting right at the start, CX is already pre-charged. Before B ever switches, CX is fully charged up. So when B switches, there's only the stray capacitance at Z which has to charge up. So that means that high to low propagates from B to Z faster than from A to Z. Okay, so they're functionally identical gates. If you draw a circuit diagram, A and B are equivalent, but actually on the silicon, the situation is slightly different and their behavior is not identical. And so there's possibilities here for optimization. And when you look at more complicated circuits, and we'll touch on these things later, for instance, look at adders, you will find that you can make some optimizations by taking this sort of thing into account. So I mentioned earlier that standard fab would have a library. So most of the big logic operations are going to be in this library. So this here is just a photocopy of a TSMC library. It's quite an old one. It's 20 years old. I've never had actually a copy of it myself, so I've just got a photograph of it here. But it's 1.8 volt, 180 nanometer CMOS library from 2001. But you can, yeah, if you look at the slides in detail, which you can't see here, there's all the standard gates. There's not inverters, NANDs, NORs. There's lots of other more complicated gates in there as well. All sorts of AOI gates. And all these gates are there in their library. So if you're doing a design, VLSI design, using the TSMC foundry, you can just go to their library and say, I like one of those and one of those. And they've done all the T-sizing and all the hard work, and you just need to plug it into your circuit and use it. And so then you can look in more detail. It's got a specific process, so that's the 180 nanometer process. And so they have all the electrical data. So they give you circuit diagrams, they give you electrical data, timing information for that particular gate. So that's great. So if you're doing a high level of design, you don't need to spend your life working out exactly how you're going to do a 5-input NAND. Somebody else has already done that. You just need to take that and put it into your library. You take it from their library and put it into your module that you're designing. Okay, so we've now gone through PMOS and NMOS transistors. We've been looking at the AOI scheme, a little bit of the OAI as well. Remember the CMOS rule. This is an important rule, and you need to know how to apply it and understand it. That if you've got a series N block, there's a complementary parallel P block, and every parallel N block has a complementary series P block. We've thought a lot about T sizing and stack depths. And finally, there's this dynamic differences between different identical gates, which is something which pops up sometimes and is important to be aware of. Right, that's the end of that set of slides. I'm going to now move on to the next lecture, which we won't finish, but we'll get partway through. Okay, we're going to look at logic styles now. That, again, we can ignore because that's the summary we just had. What I want to do is just first of all talk about next week. So next week, again, we've got a lecture on Friday, which my memory is in the Kelvin building, and of course, it's a smaller lecture theatre in this one, and there's more students in the lecture theatre, so I don't think there's room for you guys to be there. If you want to turn up at 10 past and see whether you can squeeze in, I suppose you could try that, because it probably will be a few seats, but not room for everyone. So I will try and do the same thing as today, put it onto Zoom for you. But what we're going to do, we'll finish off the lectures I'm about to start, set a notes I'm starting, but we've also got a tutorial. So the tutorial questions are on the Moodle, so you should be able to see them. They've been there ever since the start of the semester. And by the end of today, you should be in a position to answer all those questions on that first tutorial. So that gives you next week to sort of go through the questions. And then next week, as well as doing the lecture, finishing off these slides here, I will go through the questions one by one and give you answers to them. But you'll find it much more helpful if you spent some time beforehand working on them. You might get stuck, that's fine. I don't mind people getting stuck and asking for help. But if you just don't look at it, you won't learn very much. So yeah, it'll be much more useful for you if you spend some time trying to figure out the answers yourself. So that's what we're doing next week. So logic styles, whether we're Sherlock Holmes or Spock or whoever. We spent a lot of time looking at CMOS. So what we want to do is look at some other logic styles which are out there. And what I want to start off with is dynamic MOS or pre-charge. Okay, so it's another way of doing logic. So a bit of introduction to that. We've seen static CMOS so far. So what we've seen up to now is, if you like, standard static CMOS. And one of the problems with that is it can lead to physically very big gate designs, especially when you've got a large P stack. And because PMOS transistors tend to be bigger anyway, that's not a desirable thing. So pre-charge logic is a dynamic circuit technique, and it can be used to eliminate the whole PMOS tree. So if you look at static CMOS, the way we draw it, you've got an NMOS tree at the bottom and a PMOS tree at the top, and the output in the middle. With pre-charge logic, you can just get rid of the whole PMOS tree. You can, of course, also, if you wanted to, get rid of the NMOS tree, if you wanted to keep the PMOS tree, which is sometimes useful. And that also is useful from the delay point of view, as well as from the size point of view. So let's see how it works. It's a bit more complicated in some ways, but because you're losing half the tree, actually the circuits are smaller. So look at NOR, and we're going to look at NOR with N inputs for the moment. So bigger NOR as we want to look at. So we've got inputs A1, A2, all the way up to AN. So now, of course, if we had this as a static logic CMOS, we would then also have our PMOS tree. And the PMOS would have our N. N can be a big number. It could be, we've seen it for 2, I suppose, but you could have 4, you can have 8. You can have lots of inputs to an OR gate. And you'd have a big, tall series of PMOS transistors that all be sized very, very big. So it'd be a huge block. So we discard that, and instead we've got 2 transistors, which I'm calling C. There's a PMOS and an NMOS. And there are clock transistors. So you can imagine there's a clock, clocks tick, so it goes up, down. So there's 2 phases, and those 2 phases in this situation are pre-charge and evaluate. So when the clock is 0, you are going to be in the pre-charge phase, and then when the clock goes to 1, reevaluate. So let's think about the pre-charge phase. So if you put the clock to 0, essentially what we've done, instead of the whole P block, we've just got a single clock transistor here now. We've added a clock transistor here on the N side. But that one transistor is going to be a lot smaller than all the PMOS transistors you're replacing. So clock is 0. What happens? This is switched off. This is switched on. So Z, which is the output, is going to be pre-charged high. Okay, because this transistor switched on. This is our VDD. So Z just immediately gets pre-charged to high. The output sitting at high at this point. Then the clock switches to high. Now at the clock edge, immediately after it switches, P is off. N, this one comes on, this clock. And this is the evaluation phase. So if all the inputs A1, A2, A3, etc., if they're all low, then Z will stay high. Because if all these are low, then they're all switched off, they're all open circuit, and so Z was pre-charged high, and it just stays high. It's completely isolated both from VDD and VSS, so it just stays high. So this depends on the charge and the capacitor is not leaking away. So yeah, that's why it's dynamic. You couldn't sit like that forever, but in a dynamic situation, it's fine. If any of the inputs A1 to AN go low, if any of the inputs go high, then that transistor turns on, or might be several transistors turn on. Then, of course, you've got a current path from Z to VSS, and Z will fall to low. So that works perfectly well as a NOR gate. That's exactly the functionality we want. So pre-charging it has given us the right functionality. Z will move in the right direction as soon as you move to the evaluate phase. So okay, so if we have a closer look here, we've got the P stack depth is now 1. So we can T-size it to 1 times our unit inverter P width, 1 times PI, which we can make, for instance, 2.7 if you want it to be completely perfectly matched. Pull down goes through the NFET. So N stack depth is 2. So that's a bit of a problem, because that means that all the NMOS transistors are T-sized at 2W. So that, although we've saved a lot of space on the P block side of things, it does double the size of the N block. So if you compare sizes for NOR 2, where the P stack depth is 2, you get some improvement, but not a huge improvement. So yeah, if you think about 2-input NOR gate, static, you would have sizing of the P block at the top, giving you transistor widths of 2 WPI. So you have 4 WPI plus your transistors at the bottom. So what we've changed that for is we've doubled the size of the N transistors, but they were smaller, so that's not so bad. So that wins. We've added these 2 transistors, but overall you gain just a little. If you had a bigger gate, you win much more. So more inputs, everything looks better. Okay, so here's the timing diagram for what we just looked at. So the clock goes 0, high, 0, high. So you have a standard clock cycle. So during the pre-charge, your inputs are moving to where your inputs want to be. As soon as you move to the evaluate phase, then Z immediately moves to where it should be. Now, of course, if Z was going to be high already, it was already there. Alternatively, it needs to be pulled down. The pull down is going to be fast because it's pulled down through the NFETs. So there's some sacrifice in time because we've got the pre-charge, but we have reduced propagation delay. So for high input, the propagation delay is effectively 0. For a low output, it's still fairly small. sorry, I'm forgetting how this slide works. So let's just go back. Right, okay. These slides were put together by David Charles a couple of years ago, and I've forgotten how this particular slide works, so we might as well go through it. So he's got the input here, is low. And then you can see if the input goes high, Z is pulled down fast at this point. Let's move on. You could, of course, do this the other way around. You don't have to throw away the P block and just keep the N block. So it's perfectly possible to make an AND gate, sorry, a NAND gate like this, where you just keep the P block for the NAND and you get rid of the large stack on the N side. Pre-charging works in the roughly the same way, but the levels are inverted. So of course, you pre-charge when C, the clock is 1 now, clock being 1, that pulls it down and you pre-charge to 0. So everything's the other way around, but basically it works exactly the same as before. And you can expand these things to any logic functions you want. I've just shown it for NAND and for NOR, but it works for any gate which you care to think of. Now, we thought about charge sharing before when we looked at NOR gate and saw that one input was faster than the other input. We get the same sort of situation here. And because it's dynamic, this can be more serious, have more serious consequences. So here we've got a slightly more complicated gate. So we've got A, B, C in parallel and D in series. So this is D ANDed with A, B, C, and of course inverted. So it's a slightly more complicated gate. And remember that every node has its parasitic capacitance. So if you look at this point X, which is the output, no, it's not the output, Z is the output, but X is the intermediate point. X also has a capacitance. Now, what's the consequence of that? So if D and only D is high during evaluation, okay, so only D is high, that means A, B, C are low. So A, B, C are low. So A, B, C are low. These things are all off. But this is on. So whatever charge is sitting at Z will be redistributed to X. Does that make sense? So when you're in the pre-charge phase, the clock's at 0, and you're charging up Z, it's pre-charged. But if transistor D is on during that pre-charge, then that charge is redistributed to X. So X charges up to, basically. And that's okay during the pre-charge, but if it happened during the evaluation stage, then you've got a problem, because during the evaluation phase, the clock goes to 1, this transistor switches off, this transistor's on, but we're saying that A, B, C are all off. So the only transistor that's on is D. And we're now in the evaluation phase. So if in the evaluation phase, D was high and moved high at that point, you've got a problem because charge that was at Z will redistribute to X. And essentially, you'll get a voltage drop. And of course, the voltage drop will depend on the ratio of the capacitance. So simple to just draw an equation with the ratio of the capacitances like so. If that drop is too big, then you can exceed the noise margin for the next gate and the whole system stops working. So that basically says you don't want, or you don't like, certain inputs moving in certain directions, okay? So D moves high during evaluation, that's a bad thing. And that makes the whole pre-charge a little bit more complicated because you've got to be very careful you don't get into this situation. So with pre-charge, you've got various advantages, various disadvantages. It can be more compact, and when you have more inputs, that is more the case. So the more inputs you've got, you save a lot of transistors. You get a lower load capacitance, which is good. It can be lower power consumption, that's good. It can be fast. Disadvantage, if an output has changed in the evaluation phase, it can't change back. You've got, basically, it can change in one direction, but not the other, if you look at it. It's sensitive to charge leakage from output to load, so you've got to be careful about its application. The charge sharing can diminish the noise margin. And you've got a clock, so it's a bit more complicated because you've got to make sure your clock is doing the right thing. And of course, the clock increases power consumption. Okay, so what I want to do is think about two inverters joined together using this pre-charged logic. And think about what happens there. So we've got our two inverters. Now remember, an inverter, you maybe wouldn't want to do this circuit actually, because you'd say, well, my normal inverter's got 2 transistors, and it's got 3 transistors. But it's just an example of the sort of problems you can get when you've got one pre-charge gate talking to another pre-charge gate. Okay, and I'm using inverters because they're nice and simple. So an inverter as pre-charge would just be a single NMOS, and then you have your clock here and here. And these clocks are going to the next inverter. So you've got 2 inverters, one inverter driving the next inverter. So here's the timing diagram. So the clocks initially during the pre-charge, clock's at 0, and we're going to set A to be high. And what happens? Well, we need to think about what happens to Z and X. So C is low, which means this is on. A initially is low, which means this is off. This is off. So we're pre-charging X. So X is pre-charged. And A can change, and that doesn't really affect anything because C is off anyway, so the current path can't go to here. So this pre-charging here just remains. Move to the evaluation phase. So the clock now switches to 0. What happens? Well, when the clock moves to 0, the output is going to go low. It's an inverter. That's what it does. Clock goes to 0. This is off. This is on. These conduct. You pull it down.